find my notes here. So there's some terminology that we kind of have to nail down first and get a really good handle on. These concepts are actually very simple, but there's a lot of terms, like definitions. And so if you don't understand what the definitions are, it's going to be difficult to actually understand what you're doing. So it's really important to get this strong foundation here. And the first thing I want to talk about is what it means for a function to be increasing or decreasing over an interval. Okay, and you all have a really good understanding of what it means to increase and what it means to decrease. So this is nothing new to you. However, we want to kind of put it in the context of a function. And so there's some things that we have to consider when we're doing that. So let me draw a picture of an increasing function, just as an example. So we have a curve and it's increasing. Why do I say that that's increasing? Okay, well, it all is your reference or your point of view. And in mathematics, just like in English, we read from left to right, okay? So as we go in this direction on the x-axis, we are increasing. Our values on the x-axis are getting larger. And notice that the function, as we move in that direction, the function is getting larger in terms of a vertical direction as well. So we're becoming larger in a horizontal way, but we're also becoming larger in a vertical way. We're going up as we move from left to right. And your reference is very important, okay? Because if I moved in this way, it would look like I was going down, right? But in mathematics, we're always, at least for functions, we're always reading from left to right, okay? So that's important, that reference. So if I'm talking about horizontally now, I've got a value here, A and B. And so I can say by the position on the x-axis, okay, here's my x-axis, let's say, I can tell that A is less than B, okay? All right, I can see that, right? Because A is to the left of B on the x-axis. So I say that A is less than B. Well, similarly, if I pass through the function, in other words, I put A into my function, I have a point here, there's a corresponding Y value that goes with that A called f of A, and then there's a corresponding Y value that goes with B called f of B, okay? And notice that f of A is less than f of B because it's below f of B, right? F of A is below f of B, so therefore f of A is less than f of B. So if you pick a interval, and it doesn't matter what interval I pick, but inside this interval, if A is less than B and therefore f of A is less than f of B, then we say the function is increasing. Okay, and I'm just looking at a piece of the function. I mean, presumably it goes further. It might start be a decreasing function over here, but just for this purpose, this segment on this interval, I'm talking about that piece. So it's increasing on the interval. Now let's look at an example of a decreasing function. Okay, this is a decreasing function here. And similarly, you can pick your A, and you can pick your B, and you can see on the x-axis that A is less than B. However, if you go to the y-axis, notice that this time f of A is greater than f of B, whereas over here f of A was less than f of B. okay? Or f of b is less than f of a, same thing, right? Well, when you have this situation, so you have 2 points, a and b, a is less than b, but however f of b is less than f of a, then that's a decreasing function. So why I'm going through this discussion about A and B is because the point is, and you don't have to know all this, okay? You don't have to know all these details. What you need to know is that it's important to read from left to right when you're looking at a function. And if it goes up as you go from left to right, it's increasing. And if it goes down as you go from left to right, it's decreasing. That's all you need to know, okay? But I am showing you mathematically what the difference is here, okay? So there's some important things about functions that are increasing and decreasing, and they are related to the derivative. This particular section is all on the first derivative test. So it makes sense that when we talk about increasing and decreasing functions, we need to talk about them in the context of their derivatives. And you'll notice that if I draw tangent lines along this curve here, so here's a tangent line, here's another tangent line, here's another tangent line. The tangent lines all have something in common. What is it that they have in common? Well, I'm going to take my, so here's a tangent line, here's a tangent line. They're all slanted in the positive direction. In other words, the tangent lines all have positive slopes. So it follows that if your function is increasing, the derivatives, in other words, the slopes of the tangent lines are positive. The tangent lines, their slopes are all positive if the function is increasing. In other words, f prime of x, the derivative is greater than 0. Okay? Remember, the slope of the tangent is just the derivative. So if you have an increasing function, the derivative on that interval is going to be positive, all the derivatives. There's not just one derivative, right? The derivative is the function. There's not just one slope. There are many slopes, but the derivative, each slope has is equal to a derivative at that point, the value of the derivative. And so it's positive for all x on the interval where the function is increasing. So the comments that I've written here in green are very important. This is what's going to help you understand the material moving forward, because this is what the first derivative test hinges on. This right here, okay? That's what the first derivative test is all about. And looking over here at the decreasing side, you can see that the derivatives now are on this side. The slopes of these tangent lines are slanted in the other direction. That means their slopes are negative, okay? This time they're all slanted this way. Over here they're slanted this way, and over here they're all slanted this way. So I can make the same comments here about the decreasing function on the interval, and that interval is, let's say, from here to here, okay? The slopes of the tangent lines are all negative on this side. Okay? So that means then that f prime of x is going to be less than 0 for all x on the interval where the function is decreasing. Okay, so this is really important to understand this. And you don't have to understand it right now, but you want to have this in your notes so you can go back when you're doing the homework and you're trying to understand what in the heck you're doing. This is the explanation right here, okay? This stuff is really not that difficult if you understand what you're doing, okay? And that's kind of what you want to strive for when you're learning this stuff, okay? So as you can imagine, when you have some intervals where the function is increasing, like not all functions are always increasing, and they're not always decreasing, but if you focus in on an interval, you can narrow it down to where they're increasing or decreasing. So the point I'm trying to make here is often a function will start out increasing, then it will turn to decreasing, and then it'll turn to increasing like that. And in that situation, there's a point at which it goes from negative to positive or positive to negative. And so you have a point where either the derivative is going to be 0 or the derivative is going to be undefined. And these places where you have that change, that turning, that's called a critical point, or a critical value, I should say. The point itself is the point, but the value where it occurs is referring to the x-axis. So with that introduction, let me move on to talking about critical values. So to understand what a critical value is, let me just draw a picture, okay? Here we have a function that starts out, and remember I'm going left to right, so it starts out increasing, then decreasing, then increasing, then decreasing, then increasing, okay? So if I have the x-axis here, and I always draw my curve above the x-axis. That's only for discussing. I mean, it doesn't have to be that way. It could cross the x-axis, but the x-axis right now is just I'm just trying to illustrate something, so I'm drawing it this way. But okay, so here is a turning point, right? And we'll call that x1. Here's another turning point, x2. And then here's another turning point, call that x3. And here's another one, x4. Okay, so on the interval, so this function is increasing on the intervals. Well, here it's increasing, right, up until that point. It's increasing on the interval from -infinity to x1. That's one place where it's increasing. It's not increasing here because it's going down, but from x2 up to x3, it's increasing again. So we'll say from x2 to x3. And then Here it's decreasing, but at x4 and then on to infinity, it's increasing again. So the function is increasing on the intervals from minus infinity to x1, x2 to x3, x4 to infinity. And this function is decreasing on the intervals, well, here from x1 down, from x1 to x2, from here to here, it's decreasing. x1 to x2. And then again, from here to here, it's decreasing. So x3 to x4. So these intervals cover the entire x-axis, but on these three intervals, it's increasing, and on these two down here, it's decreasing. Okay, and you can kind of see that. This isn't complicated, right? What's more difficult is identifying the intervals than just to notice, oh, it's increasing, then it's going down, then it's going up, then it's going down. Remember, when they're asking you where in mathematics, they're always talking about the x-axis. So if I say where is the function increasing, you might be able to recognize that it's from here to here, but you have to know that when I ask the question where, I'm looking at the x-axis, so it's from here to here that it's decreasing, and then from here to here. So your answer to the question where is always on the x-axis, okay? And I should say, I'll write that down. And I should be careful about when I say always, what I mean by is for a function, right? When you're talking about a function and you want to know where something happens, you're always looking for the x-axis, okay? All right, so back to the question, what is a critical value? Well, a critical value is where it goes from increasing to decreasing, where there's a change or something important is happening, okay? So the critical values for this function are right here, right here, right here, and here. But when I say critical value, what I'm talking about is an x value. A critical point is the actual point itself. A critical value are the x values that correspond to those points. So the answer here is the critical values are where the function, for our example, there are other critical values that I'll talk about later, but the critical values are where the function, for our example, has a turning point in other words, the derivative is 0. F prime of x equals 0. This occurs at x1, x2, x3, and x4. So again, there's the derivative coming into play again, okay? And if you look here, why is the derivative 0? Well, the tangent line, the slope of the tangent line is the derivative, right? And you'll notice at the top or at the bottom of these little hills, so here we have a hilltop, the tangent line is horizontal. And at this little dip here in the valley, the tangent line is horizontal, and same up here, okay? And the slope of a horizontal line is 0, right? So let me write that down. Note f prime of x equals 0 means the slope of the tangent is 0, and horizontal, a slope 0 means that you have a horizontal line. A 0 slope means you have a horizontal line. Okay, your line is horizontal if you have a 0, if the tangent, I'm sorry, if the line is flat, horizontal like that, your slope is always 0. So in this case, since we have tangent lines, the derivative is 0 because the derivative is the slope, right? Okay, there's a lot going on here. It's all connected. But again, the derivative is a very important concept because it shows you how a function is behaving. And I know a lot of you are business majors, if not all of you, because this is the course that's required for business majors. But anyway, I'm not a business person, but just as a real basic example, why would we be interested in how a function is changing? Well, a company would want to know, like say they have a model for profits. They would want to know, when is the profit going to be increasing? When is it going to be decreasing? Same thing for revenue or cost. You know, they're going to be analyzing different models to, and they want to know, when is it going to be going from, suddenly there's a change from increasing to decreasing. You want to be alerted to that situation. So you're paying attention to things like derivatives and stuff like that. So that's why it's important, I suppose. Of course, I can't comment beyond that because I'm just a math person, but I wish I had more knowledge of this since I do teach business majors so much. But anyway, so there you have it. We've got increasing and decreasing is important to know about, and also critical values, because that's where you have a change occurring. Now, I mentioned earlier that there's some other situations. Normally, a critical value occurs when the derivative is 0, but another example would be when the derivative is undefined. And let me show you an example like that. Okay, so looking here, let's say we have, oh, let me get black. I like black. Say we have a graph here, and we have some function that looks like, I'm going to put it over here. All right. So you can see that something is happening here. What this, right, this spot right here, that's some constant c, let's say. Here's to the left, so on minus infinity up to our constant c, the function, we'll call it f is decreasing. And then on our interval from c to infinity, so on c to infinity, f is increasing. And I hope you can see that. Here, as we go from left to right, we're going down, 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 down. And then we're going up, 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 up. So there's a change that occurs there. So C is a critical point. But the derivative at C is not 0. Rather, it is undefined. Okay. You have a corner there. So remember when we talked about differentiability, a function was not differentiable at those spots where you have a corner like that, okay? So C is a critical point, but the derivative is undefined rather than 0. So in this example above, we have these changes are occurring, but the slope is kind of a smooth curve, and so you have a horizontal tangent line. However, down here, we do have a change. It's decreasing, and then suddenly it's increasing, but that derivative does not exist. Why? Because you go from having a negative slope to suddenly, in an instant, switching to a positive slope, and there's no gradual curve like that. So we have an undefined derivative. But C, this spot on the x-axis, is still a critical point. And that's so let me basically give you the bottom line, and I'm running out of room on this page, so I'm going to switch over. I'll give you a moment to finish writing if you need that. Any questions here before I move on? I think that's a good sign. I hope it is, that I'm making sense to you all. Okay. So the bottom line is, a point on the graph of a function is said to be a critical point if a critical point, and I should put C in here, if f prime of C is equal to, and I should say a point C f of C. I'm kind of being loose with my language here. Forget this, sorry, I'm just kind of messing this up. Okay, a point C f of C on the graph of a function f is said to be a critical point if the derivative f prime evaluated at C is equal to 0 or is undefined. And I gave you an example of each situation. So either the derivative is 0 or the derivative is undefined. Either way, if you have that, then you have a critical point. And a critical value is the x value of the critical point. So note, CF of C is the critical point and plain old C is the critical value. And honestly, I'll often use these words interchangeably, but you'll know I'm just talking about, either I'm talking about a point or I'm talking about the x value of the point, but either way, it brings you to the same spot, okay? So sometimes I get loose with my language, I'll interchange critical point, critical value, but you know what I'm talking about. I'm talking about that spot where the derivative is either equal to 0 or where the derivative is undefined, okay? So these three things that we've introduced today, or that I've introduced, are the notion of a function being increasing, decreasing, and the notion of a critical point or a critical value. Those are very important foundational concepts for the work that we're going to be doing in this chapter 3, okay? Let's look at some examples. Okay, we've been talking a lot about definitions and theory. I think where it really starts to make sense is when you start doing examples. So I'm going to start out with the most basic, simple of all functions, the linear function. So find the critical points and determine on which intervals the function is increasing or decreasing. Okay, and I just want to remind you back to the very first page when I started discussing this. Remember, increasing functions, the derivative on the interval is greater than 0, and for decreasing functions, the derivative is less than 0. So it's really important. And then the critical points are where the function is either equal to 0 or undefined. So this is what we're going to be looking at. And this is why this whole thing, this whole section is on the first derivative test, because we're taking a derivative for a function and looking at it to see where the function is increasing, where is it decreasing, where is it changing, like a critical point. And so that's really what we're doing here. So example 1, our function is negative 3x plus 2. Okay, this is a very simple function. This is a linear function, right? It has a slope of negative 3 and an intercept of 2. So I can take a look at that function. And something like this. There's the intercept. And I'll try to draw a straight line here. Now, just by looking at that picture, I know right off the bat that is a decreasing function, right? Well, let's look at the derivative to see how we know that it's a decreasing function, okay? So I'm going to take the derivative of this thing. And the derivative of a linear function is always its slope. So my derivative is negative 3. Now, that is a constant function. So this function will always be negative 3. It's never 0. Since negative 3 is never 0, this function has no critical point. And negative 3 is never undefined either. It's negative 3. It's always defined to be negative 3. So it's never 0 and never undefined. All right, so right off the bat, this function has no critical points. And we can see from the graph, it never turns and it never has a point, a sharp point or a break. It's just a smooth straight line that's always decreasing. And that's the other point. Note f prime of x is negative over the entire x-axis. And the x-axis is an interval also. It's from minus infinity to infinity, right? In interval notation, that's the x-axis, minus infinity to infinity. So it's always negative, therefore the function is increasing, or decreasing, I'm sorry. F is decreasing. And you can see that with your own eyes. As I go from left to right, my function is going down. And as I can see, the slope of every tangent line, which is always going to be negative 3, because the tangent lines are lining up with the line itself. And that's why it's the constant. And that's why the tangent lines have slope negative 3, which happens to be the same as the linear function. Okay? So this is a very simple example of how the derivative comes into play here when we're analyzing functions. Now, it's not always going to be the case that you can easily graph your function. So sometimes you're going into it blind. But for right now, with these simple examples, I want to graph them just to show you what's going on here. Okay? Any questions on that? All right, moving on to the next example. So I'm going to be doing the same thing. I'm looking for critical points and I'm looking for increasing, where the function is increasing, where is it decreasing. And I had an example here. I've kind of like I've been doing this off the top of my head and I haven't been following my notes here. So let me just take a moment to find out where my notes are. I had a function all figured out here. Oh, here it is. Okay. So the function that I want to look at now is 2x squared plus 6x minus 20. Okay, this is not a linear function. This is a quadratic function. Notice we have an x squared in here. So the degree, this is a polynomial of degree 2. That's a quadratic function. So it's a parabola. And I'm not going to take the time to figure out what the vertex and go through that whole process of graphing it because that's not my main point here. But we do know it's a parabola and we do know that it opens up because this constant here is positive. So we know I'm not going to graph it. I'm just going to draw a picture of a parabola just to kind of give you, it has a vertex. And you can see that this vertex, which by the way is not too hard to find, it's minus b over 2a. And so for our example, it's minus 6 divided by 4. So it's negative 3/2, okay? So we know that that's the vertex there. This is the x value. And then we have to plug this in to find the y value, okay? Which I will do in just a moment. But let's talk about the first derivative now, because this is the main point of this chapter is the first derivative test. So I'm going to find the derivative of my function. 2 times 2 is 4x plus 6. Okay, so this is the derivative. Now I want to know, when is this going to be 0? So set the derivative equal to 0 and solve for x. So I go ahead and do that. 4x plus 6 is equal to 0. And I'm going to subtract 6 from both sides to solve for x. And I get 4x equals minus 6. And then I'm going to divide both sides by 4. And x equals minus 6/4, which is minus 3/2. And as you can see, that's exactly what I got over here. Here I was just using the quadratic formula that shows you for quadratic function, the vertex always occurs at minus b over 2a, where this is a, this is b, and this is c. And I used that formula because I just knew it by heart, but I found it here as well, setting the derivative equal to 0, which makes sense, right? Because this is a critical point. Notice that the tangent line is flat, and that means that f prime of x equals 0. Okay? Well, that's exactly what I did. I took f prime of x, which is 4x plus 6, set it equal to 0, and I got that x is equal to negative 3/2 right there. Okay? So what that says is the function is decreasing, and then suddenly here it changes to increasing, and that's a critical point. Okay? So the way I interpret this answer here is this means negative 3/2 is a critical value. Okay, as I said, I use the term critical value and critical point kind of interchangeably. When I say value, I'm just talking about the x value. When I say point, I'm talking about the whole point. So let's go ahead and find the y value. How do we do that? To find the y value, plug negative 3/2 into the original function. So I'm going to do that. And you will, so f of -3/2 equals 2 times -3/2 squared plus 6 times -3/2 minus 20. Okay? Any questions so far? See what I'm doing? So when I calculate that, and I did this earlier, so I know the answer is minus 49/2, which is, you can think of it as -24 1/2. Okay? So this means that -3/2 is a critical value, and the critical point is -3/2, and I'll just put -49/2 there. This is the critical point. All righty, so that's a lot of information that we're getting just from the first derivative, right? And what this tells us is that when you have a turning point like that, it's called a minimum or a maximum, and it may not be the absolute minimum or maximum, but it is a relative maximum or minimum. So let me just talk about that concept for a minute here. I'm going back to my original example. Where's my page? Okay, let's look at this right here. This function here has no maximum and no minimum. Why do I say that? Well, it can't have a minimum because notice on the left here, it goes down, 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 down forever. It never reaches bottom, right? That arrow indicates that it's going down forever, okay? It never reaches bottom, so it can't have a minimum. Similarly, this side, it goes up and up and up forever and ever. It can never reach a height. There's no maximum. There's no limit. It just keeps going on forever. So this particular function has no maximum or no minimum. However, if I look here, this is a hilltop. So if I just focus in on this area right around here, that has a maximum. It's called a relative maximum. In other words, relative to other points around it. Another word for a relative maximum is a local maximum. In other words, locally, this is a high point. Just like locally, this is a low point. Locally, this is a high point, and locally, this is a low point. So we can talk about maximum or minimums, even if the function doesn't have a max or min. We can talk about relative max or mins, and equivalently local max or mins, okay? So that's what I'm going to switch to now. Going back to our example. Where was that? Oh, here. Going back to this example, this has an absolute minimum, right? And if I look at the x-axis, pretend I didn't have this picture here. How would I analyze this without having a picture? Okay, because not always are you going to have a graph for your function. Let me just show you for the x-axis. So on the x-axis, this is a critical value, -3/2. We showed was a critical value because we did the first derivative. We set it equal to 0, and then we got -3/2. So here's my critical value. And what happens at a critical value is a function changes from either increasing or decreasing, or from decreasing to increasing. So something's changing there. Now, if we're not, we can see what's happening, but if we don't have this picture, pretend we don't have this picture, we need to like pick a point here to tell if it's increasing or decreasing, because I can't see this over here. I know that it's either going to be increasing or decreasing. I know that because this is the only critical value. And the critical values divide up your x-axis into all the intervals where it's increasing and decreasing. So we have two intervals here. We have this interval and we have this interval because there's only one critical point. If you have one critical point, your x-axis is divided into two parts. Here's one and here's the other. So all I have to do is pick a point here, test it, see if the derivative is either positive or negative, and then that'll tell me if it's increasing or decreasing. I already know the answer, of course, because we have that picture up here, but just pretend we don't know the answer. And then similarly over here, I've got to pick a point, test it, and then I'll know, is it increasing or decreasing? So this is really kind of what the first derivative test is all about. So I'm going to write this down because you're going to need to revisit this to understand what's happening. So this critical point divides the x-axis into two intervals. We pick a point from each interval and check the derivative for that point. If it's positive, the function is increasing. If it's negative, it's decreasing. Okay, so what is any point here? Well, this is -3/2, which is -1.5. So if I pick -2, that will work. So I'm going to test x equal -2. So f prime of -2 is equal to, well, here's my derivative, and I'm going to write it up here. F prime of x, remember, was 4x plus 6. Okay, so I plug in a -2. 8 times -2 is -8, plus 6 is -2. It's negative, so I'm going to put a negative sign there to show me it's decreasing, okay, on this side. Now I'm going to do the same thing over here, and notice 0. I always like to pick 0 if it belongs in the interval, because 0 is easy to calculate. So I'm going to test over on this side x equal to 0, and f prime of 0 is equal to 4 times 0 plus 6, which is 0 plus 6, and that's positive. So this is positive. Okay, so it's increasing. And that's exactly what, so here we don't have the graph. We just know it's decreasing on this side and increasing on this side. And you can look at the picture now over here. It's decreasing and then increasing. So here we're just testing points. We're just testing the first derivative. It's negative, so it's decreasing. Here it's positive, so it's increasing, okay? So the point of this is you don't need the graph to test where it's increasing and where it's decreasing. All right, let's see, we're done. We're done, great, that's the end of class. We'll keep doing some more examples next time.